Hello everyone. Now our next chapter is structure and bonding. Introduction. The properties of organic compounds can be correlated to their structures. In other words, the structure of organic compounds help us to understand their chemistry. By structure we mean how the various atoms in a molecule are linked to one another and what is their relative orientation in the space. Organic compounds essentially contain carbon and hydrogen atom. Occasionally heteroatoms such as oxygen, nitrogen, sulfur, phosphorus and halogen may also be present. The various atoms in an organic molecule are held together by covalent bond which may be single, double or triple bonds. In addition, these covalent bonds may form straight chain or rings of various sizes which may be either homocyclic or heterocyclic. Each one of them may either be alicylic or aromatic. A covalent is formed by overlapping of orbitals. The carbon atom does not use pure atomic orbitals but uses hybridized orbitals for forming these covalent bonds. In this unit, we shall discuss in detail the different types of hybridization involved in organic compounds. Besides this, we shall also discuss the different types of covalent bond and their effect on the properties of organic molecule. Next is hybridization. The ground state electronic configuration of carbon is 1s2, 2s2 and 2p2. Since ground state carbon has only two half-filled atomic orbitals, therefore it should form only two covalent bonds, that is, it should be divalent. But in all its compounds such as CH4, CCl4, C2H6, C2H6, etc., carbon forms four bonds and hence it is tetravalent. Now the question arises, why should carbon form four bonds when it has only two half-filled atomic orbitals? To answer this question, let us compare the amount of energy released in forming CH2 and CH4. We know that a typical CH bond energy is about 418 kJ per mole. The reaction of carbon with two hydrogen atoms to form CH2 should liberate approximately 836 kJ per mole of energy. Alternatively, if the carbon atom is to form four bonds, it must have half-filled atomic orbitals. This is possible if we assume that one of the two s orbitals get unpaired and it is promoted to the vacant 2pz orbital. Therefore, the electronic configuration of carbon in the first excited state is 1s2, 2s1, 2p3. This is clear that the formation of CH4 is about 1271 to minus 836 is equal to 435 kilojoule mole energy, thermodynamically more favorable than formation of CH2. It is because of this reason that carbon show tetravalency. Why does carbon undergo hybridization? The concept of hybridization explains how carbon form equivalent tetrahedral bonds. It does not answer why it does so. To answer this question, let us examine the shape of atomic orbitals that mix and the hybrid orbitals that result. The shape of the hybrid orbitals obtained by mixing s and p orbitals is like that of a p orbital, except that the two lobes are unequal as shown in the figure 1.1. The larger lobe participates in the bond formation while the smaller lobe does not. Since the size of the larger lobe is always bigger than individual s and p orbitals taking part in the hybridization, hybrid orbital always form stronger bonds. It is because of this reason carbon always undergo hybridization prior to bond formation. Types of hybridization. Depending upon the number and the types of orbitals merging together, carbon undergo the following three types of hybridization. First is sp3, second is sp2 and last one is first is sp3 or tetrahedral hybridization. As stated above, on this type of hybridization, 1s and 3p orbitals combine to form four equivalent hybrid orbitals. Since these four hybrid orbitals are directed towards the corners of regular tetrahedron, therefore this type of hybridization is also called tetrahedral hybridization. All saturated compounds of carbon such as alkanes, cycloalkanes involve sp3 hybridization. Now we will discuss the shape of methane molecule. In CH4 molecule, carbon is sp3 hybridized. Each of the four sp3 hybrid orbitals then overlap with one s orbital of four hydrogen atoms to form four sp3 CH sigma bond as shown in the figure 1.2. Thus, methane in tetrahedral molecule with each CH bond angle equal to 109 degree 28 minutes. All the four bonds of methane are equivalent and are 110 picometer long. Each CH bond has a bond dissociation energy of 416 kilojoule per mole. Next Next is sp2 or trigonal hybridization. In this type of hybridization, 1s and 2p orbitals, say 2px and 2py, combine to form three equivalent sp2 hybrid orbitals, while the third 2p remains unhybridized. The three sp2 orbitals lie in the plane and are directed towards the three corners of an equivalent triangle. That is why sp2 hybridization is also called trigonal hybridization. The unhybridized 2pz orbital is, however, perpendicular to the plane containing these three sp2 hybrid orbitals. All compounds of carbon which contain CC bond, such as alkene, arenes, etc., which involve sp2 hybridization. Now we will discuss the shape of ethane or ethylene CH2 molecule. In ethylene molecule, each carbon in sp2 hybridized. Now one of the three sp2 hybrid orbitals of each carbon overlap mutually along their internuclear axis to form sp2 carbon-carbon sigma bond. The remaining two sp2 orbitals of each carbon overlap with one s orbital of two hydrogen atoms to form in all four sp2s CH sigma bonds. Further, since all the three sp2 orbitals of each carbon lie in a plane, the two carbon atoms and the four hydrogen atoms also lie in a plane. Each carbon atom is now left with one unhybridized 2pz orbital which is perpendicular to the plane of carbon and hydrogen atoms. These two 2pz orbitals are parallel and hence overlap sideways to form a pi bond that will be shown on the figure 1.4a. Thus the pi bond is perpendicular to the plane of carbon and hydrogen atom. Further, the electron cloud of the pi electron consists of two equal halves, one lying above and other lying below the plane. From the above discussion, it follows that the carbon-carbon double bond consists of two different bonds, that is, a sigma bond and a pi bond. Whereas the sigma bond has a symmetry axis along the carbon-carbon bond, pi bond does not. However, the pi bond is dissected by a plane containing the two carbon and four hydrogen atoms. The bond energies for the carbon-carbon single bond and carbon-carbon double bond have been determined to 347 kJ per mole and 598 kJ per mole, respectively, giving a bond energy of 251 kJ to the pi bond. Thus, a pi bond is a weaker bond than the sigma bond. Being weaker, a pi bond easily breaks in the chemical reaction. Therefore, it is this pi bonds which is responsible for the chemical reactivity of ethene and other alkenes. Now our next topic is bond length. We know that during the formation of a chemical bond, the combining atoms approach each other. As they come closer and closer, the potential energy of the system keeps on decreasing until a certain minimum distance between the two atoms. The potential energy of a system becomes minimum and the attractive and repulsive force just balance each other. The minimum direction between the centers of the nuclei of two bonded atoms at which the attractive and the repulsive forces just balance each other and the potential energy of the system become minimum is called the bond. It should be noted that because of constant vibration of the bonded atoms, the distance does not remain constant. Thus, the bond length is actually the average distance between the nuclei of the bonded atom. It is expressed either in angstrom units or picometers and can be determined with the help of physical methods such as X-ray diffraction, neutron diffraction, and spectroscopic methods. The magnitude of bond length between the two atoms X and Y remains constant and is independent of the nature of the molecule for the same class of compound. For example, the CH bond distance remains to be 110 picometer or 1.10 angstrom in large number of saturated compounds such as methane, ethane, propane, etc. The bond length of some typical bonded are listed as below. The magnitude of the bond length depends upon the following factors. First is the size of the atoms. As the size of atom increases, the bond length increases in the same order. For example, the size of the halogen atom increases, the bond length of CX bond increases. Firstly, CF is less than CI. Second is multiplicity of a bond. As the multiplicity of bond between two atoms increases, the bond length decreases. For example, CC bond length is 1.54 angstrom, while that C double bond is 1.34 and that of C triple bond is 1.20 angstrom. Third factor is the type of hybridization. Since a p orbital is much bigger in size than s orbital of the same shell, therefore As you go from sp3 to sp2 and sp, the percentage of p character decreases. Accordingly, the size of the orbital decreases in the same order, that is sp3 hybridized, then sp2 and then sp. Since a bigger orbital form a longer bond, therefore cc single bond length decreases in the order sp3 then sp2 and then sp. Further, since the sideways overlapping of 2p orbitals to form pi bonds brings the two carbon atoms closer to have an optimum degree of overlap, therefore a single bond is longer than a double bond, which is in turn is longer than a triple bond. Similarly, a CH bond may be formed by overlapping of sp3, sp2 or sp orbital of carbon with an s orbital of an hydrogen. Therefore, as the size of the hybrid orbital decreases, the length of CH bond decreases accordingly, that is sp3 then sp2 and then sp. Next is bond angles. Polyatomic molecules contain more than one covalent bond. Each covalent bond in turn is formed by overlap of atomic or hybrid orbitals. Since atomic orbitals except s orbital and hybrid orbitals are directional in nature, therefore covalent bond make angle between them. Thus, the angle between any two adjacent covalent bonds in n polyatomic molecules is called the bond angle. Like bond lengths, bond angles are also measured by X-ray diffraction spectroscopic method. Further, because of the constant atomic vibration, the bond angles thus measured are actually average bond angle. In general, the bond angles depend upon the type of hybridization, the number of shared and lone pair of electrons around the central atom in a molecule. Since the magnitude of the repulsion between these pairs decrease in the order lone pair, then lone pair, bond pair, and then bond pair, bond pair. Therefore, as the number of lone pair increases, distortion from the regular geometry occurs and the bond angle decreases from their expected values. Okay. Next, our topic is bond energy. Whenever a covalent bond is formed, some amount of energy is always released. Conversely, the same amount of energy will have to be supplied to break the bond. The amount of energy required to break 1 mole of bond between two atoms is called bond dissociation energy. It is symbolized by D and it is represented in kilojoule per mole or kCl per mole. For example, 435 kilojoule of energy is required to break 1 mole of hydrogen molecule into individual atoms. In fact, bond dissociation energy is a measure of strength of the bond. Evidently, greater the bond dissociation energy, greater is the strength of the bond. However, in case of polyatomic molecules, bond energy may have two different meanings. First, bond dissociation energy, which is the energy required to break 1 mole of the particular bond, and second is bond energy, which is the average energy of different bond dissociation energies for all such similar bond present in a molecule. It is symbolized by E. Let us now illustrate the difference between these two terms by considering an example of methane molecule. If we begin to remove the 4 hydrogen atom one at a time by breaking the CH bond, we will have 4 values of bond dissociation energy. If we will remove 1 hydrogen atom from the methane, we will get bond dissociation energy is 427. If we will remove 2, we will get 439, and similarly. The question arises why do we get 4 different values of bond dissociation energy when we are breaking a CH bond in each step? This is due to the reason that bond dissociation energy not only includes the energy required to break a particular bond but also includes the energy changes which accompany the process of hybridization of the carbon atom, which is different from each step. Evidently, the large bond dissociation energy per mole of CH bond in methane is 416.25 kilojoule per mole. Since in general the bond energy depend upon the following factors. First is size of the atom. As the size of the atom forming the covalent bond increases, greater will be the bond length and hence smaller will be the bond energy. For example, the bond energies of the CX bond decreases from CF to Ci as the size of the halogen atom decreases from fluorine to iodine. Second is multiplicity of bond. As the multiplicity of bond increases, the bond length decreases and the bond energy increases. Third is type of hybridization. As the percentage of S character increases from sp3 to sp2 and sp, The size of the hybrid orbital decreases. As a result, the bond energy decreases and hence bond energy increases. In contrast, a pi bond is formed by sideways overlapping of the two p orbitals. Since the extent of overlap in sideways overlap is low, a carbon-carbon pi bond is always weaker than a carbon-carbon sigma bond. A carbon-carbon double bond is, however, stronger than a carbon-carbon single bond, since it consists of strong sigma bond and a weak pi bond. In similar way, a carbon-carbon triple bond is still stronger than a carbon-carbon double bond. Next is localized and delocalized bonds. A covalent bond is formed by overlap of atomic or hybrid orbitals. The electrons which form these bonds can be either localized or delocalized. If the electron forming a covalent bond spend most of their time in between the space between the two participating atoms, such electrons are called localized electrons and the bond formed by them is localized bond. In contrast, if the electrons forming a covalent bond are not confined to the space between the two bonding atoms, the electrons are called delocalized and the bond thus formed is called the delocalized bond. Since the electron forming all type of sigma bonds such as sp3 bonds of methane, sp2 bonds in ethane, sp bonds in acetylene are localized between their respective participating atoms, these are called localized electrons and the bond formed by them are localized bond. Thus all type of sigma bonds are localized bond. In contrast, electrons forming pi bonds may or may not be localized. For example, the electrons forming the pi bond in ethylene are confined to the space below and above the CC sigma bond and also localized. However, the electrons of the 2 pi bond of acetylene and are delocalized since the electron forming the pi bond in the plane of the paper do not remain confined to the region below and above the carbon-carbon sigma bond, and similarly the electrons forming the pi bond to the plane perpendicular to the plane of the paper do not remain confined to the region in front and back of carbon-carbon sigma bond. Instead, these four halves of electron clouds merge together to form a cylindrical electron cloud, in which the four electrons of 2 pi bonds in acetylene are completely delocalized. Now our next topic is van der Waals interaction. It is well known that gases do not obey ideal gas equation, that is PV is equals to nRT. And second, non-polar gases such as methane, neon, argon, nitrogen, O2, etc. can be considered first to liquid and then to solid state. In order to account for this observation, van der Waals, a Dutch chemist, proposed the existence of some sort of attractive force between the molecules of non-polar compounds. He named these forces as van der Waals interaction. These forces operate only at small distance and result from induced polarization of the electron clouds in the molecules as discussed below. Normally, in a non-polar molecule, the center of negative and positive densities coincide with each other and hence these molecules do not have any dipole moment. However, because of the constant random motion of the electron cloud around the nucleus, it is expected that at any instant of time, this electron cloud may get slightly distorted due to the collision of molecules or by some other factors. Consequently, at that instant of time, the center of positive and negative charge densities do not coincide and a temporary dipole moment is induced in one molecule. This temporary dipole moment in one molecule causes a nearby molecule to adopt a temporary opposite dipole moment and a small attraction is induced in the molecule. These induced dipole attraction are also called London forces or the dispersive forces. Although these temporary dipoles have only a transitory existence and are constantly changing, but the combined effect of these large number of small attractive forces is significant and is reflected in their properties. These forces are weak and are maximum in solids and maximum in gases due to the difference in the intermolecular distance into cases. In other words, there are short range forces and operates only between those portions of molecules which touch each other, that is between surface of a molecule. Evidently, greater the surface area of the molecule, stronger are the van der Waals forces of attraction. This helps in explaining the effect of the molecular size and shape on the physical properties of many substances. For example, the boiling point of an alkane shows a regular increase per CH2 group as ascend in the homologous series. This is due to the reason that the molecular mass of alkane increases. The molecular size and the surface area also increases accordingly. As a result, the magnitude of the van der Waals forces of attraction increases, and hence the boiling point of n alkanes increases as the molecular mass increases. Amongst isomeric alkanes, the branched chain alkanes has invariably the lower boiling point than the corresponding n alkane. This is due to the reason that with branching, the shape of the molecule tends to approach that of sphere. As a result, the surface area of the branched isomer decreases. Due to lesser surface area of these molecules, the van der Waals forces of attraction operating between their molecules become comparatively smaller, and hence lesser amount of energy is required to overcome them. As a result, the boiling point of branched chain isomer are lower than those of corresponding n alkanes. Next is van der Waals repulsion. As discussed above, the magnitude of the van der Waals forces of attraction increases as the distance between the molecules or the non-bonded atom increases. However, this attraction is maximum when the molecules or non-bonded atoms are at a minimum distance that they touch each other. If they are forced closer than this minimum distance, then these attractive forces turn into repulsive forces are called van der Waals repulsions. If the sum of the van der Waals radii between two non-bonded atoms or molecules is less than the distance between them, then the attractive forces are turned into repulsive. For example, consider the both form of cyclohexane. The distance between the flagpole hydrogen is just 183 picometer, which is less than the sum of van der Waals radii of two hydrogen atoms, that is 240 picometer. And hence both form of cyclohexane is less stable than the chair form, in which no such repulsions exist. Now next is a type of van der Waals attractions. We have discussed above that van der Waals forces of attraction due to induced dipole interaction occurs in non-polar molecules. However, in polar molecules, van der Waals forces of attractions may originate from dipole-dipole and dipole-induced dipole interaction as discussed below. First, dipole-dipole interaction. In case of polar molecules, the van der Waals forces are mainly due to the electrical interaction between positively charged ends of molecules called dipole-dipole interaction. For example, gases such as NH3, SO2, HCl, HF, etc. have permanent dipole, as a result of which there is appreciable dipole-dipole interaction between the molecules of these gases. The magnitude of this type of interaction depends upon the dipole moment of the molecule concerned. Evidently, greater the dipole moment, stronger is the dipole-dipole interaction. Because of their attractive forces, the gases can be easily liquefiable. Second is dipole-induced dipole interaction. A polar molecule may sometimes polarize a non-polar molecule which lies in its vicinity and thus induce polarity in that molecule, just as a magnet induces magnetic polarity in neutral piece of iron lying close by. The induced dipole then interacts with the dipole moment of first molecule, and thereby the two molecules are attracted together. The magnitude of this interaction evidently depends upon the magnitude of the dipole moment in the polar molecule and its polarizability of non-polar molecule. The solubility of the dipole moment of the polar molecule and the polarizability of the non-polar molecule. The solubility of inert gases in H2 increases from Hn to Rn due to corresponding increase in magnitude of the dipole induced dipole interaction, and the polarizability of the noble gases increases with increases in the size from helium to Rn. Now our next topic is inductive effect and the field effect. Whenever an electron withdrawing group such as chlorine NO2 is attached to the end of the carbon chain, the sigma electrons of CCl bond are attracted or displaced towards a more electronegative chlorine atom. As a result of this displacement, chlorine atom requires a small negative charge and C1 acquires a small positive charge, which is shown in below. The small positive charge on C1 attracts the sigma electrons of C1-C2 bond towards itself. As a result, C2 will acquire a small positive charge, but this charge will not be smaller than O1 C1. Similarly, C3 will acquire a small positive charge that will still be smaller than on C2. This effect can still be transmitted further, but the intensity goes on decreasing considerably with distance. This type of sigma electron displacement along a saturated chain of carbon atom due to the presence of a polar covalent bond is called an inductive effect or simply I effect. Sometimes inductive effect is also called a transmission effect or T effect. Next is type of inductive effect. It is of following two types: minus I effect and plus I effect. First is minus I effect. If the heteroatom attached to the end of the carbon chain is more electronegative than carbon, or the substituent attached to the end of the carbon chain is electron withdrawing or electron attracting, the inductive effect is called minus I effect. The extent of minus I effect, however, depends upon the electronegativity of the heteroatom or the substrate. Greater the electronegativity, stronger is the minus I effect. The decreasing order of the minus I effect of some common atoms in the substituent relative to the hydrogen is minus Nr3 positive greater than minus Sr3 or etc. Second is if the heteroatom attached to the end of the carbon chain is less electronegative than carbon, or the substituent attached to the end of the carbon atom is electron donating or electron releasing, the inductive effect is plus I effect. The only electron donating groups are groups with a formal negative charge, atoms of low electron negativity such as lithium, Si, Mg, etc., and alkyl group. By far the most important example of electron group having electron donating inductive effect, that is plus I effect of the alkyl group. The magnitude of the plus I effect, however, depends upon the nature of the alkyl group. The more highly substituted alkyl group, the greater is its ability to donate electrons, and however stronger is its plus I effect. Thus, the decreasing order of plus I effect of some alkyl group relative to that of the hydrogen which attached to the saturated carbon chain follows the order as is tert butyl followed by isopropyl, N-propyl, ethyl, and methyl. This order of plus I can be easily explained on the basis of hyperconjugation, which we will discussed later in this unit. Next is the characteristics of inductive effect. In first, inductive effect involves only displacement of sigma electrons and occurs in polar single covalent bond. Second is the inductive effect is permanent effect and cannot be reversed. Third is the inductive effect decreases progressively as the distance between the carbon atom and the electron withdrawing or the electron donating group or the group increases. Fourth, the displaced electrons do not leave their orbital. Instead, only a little distortion of the orbitals occurs, which causes polarization as shown below. Fifth, depending upon the electron donating or electron withdrawing ability, different atoms or different groups cause polarization of the covalent bond to different extents. Next is application of the inductive effect. First is stability of reactive intermediates. The relative stability of free radicals, carbocations, and carbanions can be explained on the basis of inductive effect. Second is polarity of covalent bond and dipole moment of organic compounds. Inductive effect causes polarization of the covalent bonds between two dissimilar atoms. Due to this charge separation, each covalent bond has a definite dipole moment. The magnitude of this dipole moment depends upon first the electronegativity difference between the two atoms forming the covalent bond. Second, the orientation of the various polar covalent bonds in an organic compounds, which are discussed below. First, electronegativity difference. Greater is the electronegativity difference between the two atoms forming the covalent bond, more polar is the covalent bond, and hence greater is the dipole moment of the organic compound. For example, the dipole moment of the following compounds increases as the electronegativity difference between carbon and its hydroatom increases. Second is orientation. Orientation of polar covalent bonds. If a molecule has two or more covalent bonds, the actual dipole moment of the molecule depends upon their orientation in space. In other words, the actual dipole moment of molecule is a vector sum of all the individual bonded moments. Okay, in CCl4 there are 4 polar Cl bonds. Due to their tetrahedral shape, the resultant dipole moment of any two adjacent CCl bond is cancelled by an equal and opposite resultant of the remaining 2 CCl bond. As a result, the net dipole moment of carbon tetrachloride is 0. In CH2Cl2, the resultant of C2CH dipole reinforced to the resultant of 2 CCl bond, and hence the dipole moment and hence the molecule has a dipole moment of 1.62d. However, in CHCl3, the resultant of the small CH dipole and one large CCl bond opposes the resultant of the remaining CCl doubles. As a result, dipole moment of chloroform is lower 1.01 than that of methylene chloride. Now let us now briefly discuss the effects of various substituents on the acidity of the carboxylic acid. First, effect of electron donating substituent, that is alkyl group. Let us compare the relative strength of formic acid and acetic acid. Methyl group present in acetic acid, due to which plus I effect increases the electron density in the OH bond. As a result, release of H positive ions from acetic acid will be more difficult as compared to formic acid. Hence, formic acid is more stronger acid than acetic acid. Alternatively, CH3 group, because of its plus effect, intensify the negative charge on acetic acid and thus destabilized to relative to formic ion. Hence, formic acid is a stronger acid than acetic acid. Second, effect of electron withdrawing group. Let us consider the relative strength of acetic acid and chloroacetic acid. The chlorine atom present in chloroacetic acid, because of its minus I effect, withdraws electron from the OH bond. As a result, the electron density in the OH bond decreases. In other words, the OH bond weakens, and thus the release of H positive ions from chloroacetic acid is facilitated related to the acetic acid. Hence, chloroacetic acid is stronger acid than acetic acid. Alternatively, Cl atom, because of its minus effect, tends to disperse the negative charge on chloroacetate ion, while CH3 group, because of their positive charge, tends to intensify the negative charge on acetate ion. As a result, chloroacetate ion is more stable than acetate ion, and hence chloroacetic acid is more stronger than acetic acid. There are some important conclusions. First, the stronger the plus I effect of the substituent or greater the number of electron donating group, the weaker is the acid. Second, the stronger the minus I effect of the substituent, stronger is the acidity. This is due to the reason that minus I effect decreases in the order. Furthermore, the number of the electron withdrawing substituent increases, stronger is the acid. As the distance between the electron withdrawing substituent from the CH group increases, the strength of the acid decreases. Third is comparison of the relative strength of alkyls. The relative strength of alkyl follows the order acetylene, that is CH3, C, triple bond CH, etc. Explanation: the plus I effect of the alkyl group decreases in the order. As we move from H to CH3 to CH3 to CH2, the electron density in triple bond CH increases, and thus in triple bond CH bond becomes stronger. In other words, it becomes more and more difficult to release a proton, and hence its stability decreases in the same order. Now we will see effect of electron donating group. Aliphatic, primary, secondary and tertiary amines contain 1, 2 and 3 alkyl group attached to the nitrogen atom respectively. These alkyl group, because of their plus I effect, tends to increase the electron density on the nitrogen atom. Consequently, all the amines can donate a pair of electrons or more readily than ammonia, and thus stronger bases than ammonia. On the basis of plus I effect of the alkyl group, the expected order of basicity should be tertiary amines followed by secondary and the primary amines. However, the actual order of basicity of amines in aqueous solution is secondary amines, then primary, and then tertiary. This is supported by the pKb value for three classes of the amines. Explanation: the reason why the actual order is different from the expected order may be explained as follows. The basicity of an amine in an aqueous solution does not entirely depend upon the electron density on the an atom, but also depends upon the stability of the conjugate acid formed by accepting a proton from the solution. The stability of the conjugate bond in turn depends upon the extent of hydrogen bonding. Obviously, greater the number of H atoms on the N atom, more stable is the conjugate bond. Thus, the conjugate acid of primary amine is more stable since it has 3 H atoms which can form H bonds. The conjugate acid of second amine is less stable since it has 2 atoms, while that of tertiary amine is the least stable since it has only 1 H atom which can form H bond as shown below. Thus, on the stability of the conjugate acid alone, the basic strength of amine should follow the order secondary, primary, secondary, and then the tertiary. Unlike electronegative effect, electromagnetic effect is a temporary effect and operates in unsaturated compounds only at the demand of the attacking agent. It involves complete transfer of pi electrons of a multiple bond to one of the bonded atoms. Consider, for example, the attack of a nucleophile to a carbonyl group. In the presence of a nucleophile, the pi electrons of the carbon-oxygen double bond are completely transferred to more electronegative atom. However, the attacking reagent is removed without the reaction being allowed to take place, the molecule reverts back to the original state. Thus, electromagnetic effect is only temporary in nature. Next is type of electromagnetic effect. Like inductive effect, electromagnetic effect is also of two types: plus I effect and minus I effect. If the pi electrons are transferred to that atom of the double bond to which the attacking reagent gets finally attached, the effect is plus I effect. For example, addition of acids to alkenes. If on the other hand pi electrons are transferred to an atom of the double bond other than the one to which the attacking reagent gets finally attached, the effect is called minus I effect. For example, addition of cyanide ion to the carbonyl group. Significance of electromagnetic effect. It may be noted that so far it has been possible to distinguish experimentally between minus I and minus I effect, but the fact that the reactivity of a molecule increases considerably upon the close approach of the reagent definitely suggests the involvement of some electronic effect such as electromagnetic effect. In certain molecules, both I and E effects operate together. Sometimes they assist or reinforce each other, and sometimes they oppose. Whenever they oppose each other, it is always the minus I. It is always the I effect which dominates over the I effect. Now we will compare the inductive effect and electromagnetic effect. Inductive effects, it will only operate in saturated compounds and at least one polar bond. It is a permanent effect and it only involves the displacement of sigma electrons. It does not require any outside reagent for its operation. Due to inductive effect, only a partial separation of positive and negative charges occurs, but ions are not formed. An electromagnetic effect, it occurs in unsaturated compounds containing at least one double or triple bond, which may or may not be polar in nature. It is a temporary effect and involves the cleavage of multiple bonds with complete transfer of shared pair of electrons to one of the bonded atom. It takes place only in the presence of attacking reagent. Due to electromagnetic effect, they occur complete transfer of electrons from the reagent to the substrate, or vice versa, and hence ions are always formed. Now our next effect is resonance. The concept of resonance or mesomerism was introduced to explain the properties of such molecules which cannot be represented by a single electronic or Lewis structure. In such cases, it has been found that the molecule can be represented by two or more electronic structures, each of which can explain most but not all the observed properties of the molecule. The real structure of the molecule lies somewhere in between all these electronic structures, which however cannot be represented on paper. Thus, the phenomena of resonance is said to occur when for a molecule we can write two or more Lewis structures which offer in the position of electrons but not in the relative position of atoms. The various Lewis structures are called contributing, canonical, or resonance structures. The actual structure of the molecule is not represented by any of the resonance structures but is a resonance hybrid of all these Lewis assets. The various resonance structures are separated by a double-headed arrow. The most thoroughly studied example of resonance is provided by the benzene. It is presented as a resonance hybrid of the following two Kuckel Lewis acid that will be shown in the structure 1 and in the structure 2. Now our next topic is resonance energy. A resonance hybrid, or we can say the actual molecule, is always more stable than any of the canonical structure, that is hypothetical or imaginary structure. This stability is due to the delocalization of the electrons and is measured in terms of resonance energy or the delocalization energy. It is defined as the difference in the internal energy of the resonance hybrid or the actual molecule and the more stable canonical structure. Furthermore, the number of equivalent structures, greater is the delocalization of the electrons and higher is the resonance energy and more stable is the compound. In case of benzene, this resonance energy has been determined to 150.62 kJ per mole. The resonance can be calculated either from heat of hydrogenation or heat of formation. Both these methods are illustrated below by taking an example of benzene. Now next is condition for the resonance. The main condition for resonance are: first, the various resonance structures should differ only in the position of electrons and not in the position of nuclei. Second, all the atoms taking part in resonance must lie in the same plane or nearly so. Third, all canonical forms should have the same number of paired and unpaired electrons. Fourth, all the canonical structures should have same or nearly the same amount of energy and the stability. Such structures are called equivalent structure and contribute equally towards the resonance hybrid. Fifth, in fact, all the canonical structure contribute towards a resonance hybrid in proportion to their relative energy and stabilities, the most stable form contributing the most. 6. The greater the number of significant canonical structure that can be written for a molecule and more nearly they are equal in energy, greater is the resonance energy of the molecule. While determining the relative stability of the different resonating structure, the following points must keep in mind. First, structure with greater number of covalent bond contribute more towards the resonance hybrid. Since formation of a bond is accompanied by release of energy, therefore structure 10 with 2 pi bonds is more stable than structure 9 and 11 which contain 1 pi bond. Hence structure 9 make greater contribution towards the resonance hybrid than structure 10 and 11. Second, structure which involves separation of positive and negative charges are of higher energy and hence contribute less towards the resonance hybrid than those which do not involve any separation of the charges. Third, in case of atoms of the second period in the periodic table, such structures which violate octet rule should not be considered. Fourth, when atoms of different electronegativities are involved, structure with the negative charge on the more electronegative atom and the positive charge on the less electronegative atom is of lower energy and hence contributes more towards the resonance hybrid than the alternate structure which the charges are reversed. Fifth point is structure with the help to delocalize the positive charge make important contribution towards the resonance hybrid regardless of the fact whether the positive charge is on less or more electronegative atom. Sixth and last point is resonance structure having like charges on adjacent atoms are of high energy and contribute little towards the resonance hybrid. Now we will discuss the properties of resonance hybrid. First, stability. A resonance hybrid is always more stable than any of its canonical structure. This stability is due to the delocalization of electrons and is measured in terms of resonance energy. More the number of equivalent resonance structure, greater is the stability of electrons and larger the resonance energy, hence more stable is the actual molecule. In other words, larger the resonance energy, more stable is the compound. Second is bond length. The bond length in the resonance hybrid on real molecule are different than those of in contributing structures. For example, all the carbon-carbon bond length in benzene are equal and are 1.39 angstrom, while each of two contributing covalent structures has two types of carbon-carbon bond length and carbon-carbon double bond length of 1.34 angstrom and carbon-carbon single bond length of 1.54 angstrom. Now we will do the main points of difference are summarized below: resonance effect and the inductive effect. Resonance effects occurs only in conjugated systems such as conjugated polynes, alpha, beta unsaturated carbonyl compounds and are aromatic compounds, whereas inductive effects occurs in saturated compounds. In resonance effects, it involves delocalization of n and pi electrons. Inductive effect, it involves displacement of sigma electrons. Resonance effect. During resonance effect, the electron pair is completely transferred and hence full positive and negative charge appear. An inductive effect. During inductive effect, the electron pair is slightly displaced towards the more electronegative atom and hence only partial positive and negative charges can appear. Inductive effect does not involve delocalization of electrons. Resonance effects are transmitted all over the length of the conjugated system without suffering much change in magnitude. Inductive effects are transmitted only over short distance in saturated chains and the magnitude of the effect decreases rapidly as the distance from the heteroatom increases. The effect almost becomes negligible beyond 2 carbon atoms from the heteroatoms. Now we will do the application of the resonance effect. First, Low reactivity of vinyl and aryl halides. As compared to the alkyl halides, vinyl and aryl halides are far less reactive towards nucleophilic substitution reaction. The reason being that due to the plus R or plus M effect, the lone pair of the electrons on the halogen atoms are delocalized over the entire pi system. Consequently, vinyl chloride can be regarded as a resonance hybrid of structure 1 and 2 and chlorobenzene as a resonance hybrid of structure 3 to 6. Due to this resonance stabilization, the carbon-chlorine bond acquires some double bond character. As a result, halogen gets firmly attached to the carbon and cannot be easily displaced. Second, high reactivity of allyl and benzyl halides. Allyl and benzyl halides are far more reactive than primary alkyl halides towards nucleophilic substitution reaction. This is due to the reason that both allyl and benzyl halides readily undergo ionization to form resonance stabilized carbocation. In contrast, the carbocations derived from primary alkyl halides are not stabilized by resonance, hence they are not easily formed. Third is acidity of carboxylic acid. The acid character of carboxylic acid is due to the release of H positive ions in aqueous solution to form carboxylate ion. Both carboxylic acid and carboxylate ions are stabilized by resonance, whereas canonical structure of carboxylate ions are equivalent and carry only a negative charge. But the canonical structure of the undissociated carboxylic acids are not only equivalent but also involve separation of charges. Since energy is needed to separate positive and negative charges, therefore carboxylate ion is much stable than carboxylic acid and is this greater stability of carboxylate ion as compared to the carboxylic acid, which is responsible for ionization and hence the acidic character of the carboxylic acid. Fourth is relative strength of acidic character of phenols and alcohols. The acidic character of phenol is due to the release of proton in aqueous solution to form phenoxide ion. Both phenol and phenoxide ion are stabilized by the resonance. In case of phenoxide ion, canonical structures carry only a negative charge, but in case of phenol, canonical structure involves separation of positive and negative charge. Since energy is needed to keep opposite charges apart, therefore phenoxide ion is better stabilized than phenol, and its greater stability of phenoxide ion over phenol, which is responsible for their ionization and hence acidic character of phenols. However, in case of alcohols, both the alcohol molecule and alkoxide ion are not stabilized by resonance. Further, alkoxide ion, due to the presence of formal negative charge on oxygen atom, has greater energy than alcohol molecule. Therefore, alcohols have a negligible tendency to form less stable alkoxide ion by releasing a proton. Thus, we conclude that phenols are stronger acids than alcohols because phenoxide ion left over the release of proton is stabilized by resonance, but alkoxide ion is not. Fifth, comparison of relative strength of ethylamine and aniline. Ethylamine is much a stronger base than aniline. In ethylamine, the plus effect of ethyl group increases the electron density on the nitrogen atom, thereby increasing the basicity with respect to NH3. In contrast, in aniline, the lone pair of electrons on the nitrogen atom get delocalized over the benzene ring. As a result, the electron density on the nitrogen atom decreases with respect to ammonia, and hence aniline is weaker base than ammonia. However, due to the plus I effect, ethylene is a stronger base than ammonia. Sixth is comparison of basic strength of ethylamine and the acetylamine. In ethylamine, the plus I effect of ethyl group increases the electron density on the nitrogen atom, thereby increasing its basicity. In contrast, the acetamide, due to the plus I effect of a minor amino group, the lone pair of the electrons on the nitrogen atom is delocalized over the carbonyl group. As a result, the electron density on the nitrogen atom decreases. Therefore, acetamide is weaker base than ethylamine. Seventh is effect of the dipole moment. The overall dipole moment of a molecule is the vector sum of the dipole moment of the all individual polar bonds present in the molecules. However, resonance may either increase or decrease the magnitude of the overall dipole moment of the molecules depending upon the nature of the polar bond present in it. For example, the dipole moment of ethyl chloride is much higher than that of vinyl chloride. This is due to the reason that in vinyl chloride, the inductive effect and the resonance effect of chlorine operates in opposite direction, thereby decreasing its dipole moment as compared to that of ethyl chloride, whereas only inductive effect operates. Now Our next topic is aromaticity, that is Huckel rule. What is aromaticity? Benzene and all these compounds which resemble benzene in their chemical behavior are called aromatic compounds. They exhibit properties which are quite different from those of aliphatic and alicyclic compounds. Some important characteristics properties of aromatic compounds are, although their molecular formula suggests a higher degree of unsaturation, yet their resistance to addition and oxidation reactions generally shown by the corresponding unsaturated aliphatic compounds. Instead, they prefer to undergo radially certain electrophilic substitutions reactions such as halogenation, nitration, and sulfonation. Their molecules are usually cyclic and generally contain free 5, 6, or 7 membered ring. Their molecules are flat as shown by X-ray and electron diffraction method. These properties, which are common to all aromatic compounds and which distinguish them from aliphatic or alicyclic compounds, are collectively referred to as aromatic character, and the phenomena is called aromaticity. The distinct behavior of the all aromatic compounds suggests that they must have some common structural features which account for their aromatic character. Many theories have been put forward from time to time to explain aromaticity, but none of them was completely successful. Of these, Robinson's six-set theory and resonance theory deserve comment here. First is resonance theory. Since benzene and other aromatic compounds have high resonance energy, therefore MgS, they were defined aromatic compounds as cyclic compounds, whereas all the other atoms take part in a single conjugate system and have high resonance energy. For example, benzene, naphthalene, anthracene, and penanthrene have high resonance energy and all are aromatic. Although resonance energy is a useful criteria, it cannot explain the aromatic character completely by itself. Second is aromatic succession theory. This theory was proposed by Robinson and Armitt in 1925. According to this theory, each carbon atom in benzene contributes one electron, and these 6 electrons form a closed loop, and it is this closed loop which is responsible for its stability and aromatic character. In the light of the above arguments, all the compounds which contain a closed loop of 6 electrons were called aromatic, and the theory was called the aromatic succession theory. Like benzene, pyridine has a closed loop of 6 electrons, and these compounds, each of the 5 carbon atoms and 1 nitrogen, contribute 1 electron each towards the aromatic succession formation. However, in 5-membered heterocycles like furan, thiophene, and pyrrole, each of the 4 carbon atom contributes 1 electron, while the heteroatom contributes 2 electrons towards the aromatic succession formation. This theory is, however, of limited application since it could not explain aromatic character of compound containing 2, 10, 14, 18 up to n electrons. Third is Huckel rule. On the basis of molecular orbital calculation, Huckel rule, a German physicist, Erich Huckel, a German physicist, in 1931 pointed out that in order to be aromatic, a compound must fulfill the following criteria. First, the molecular or ion must have a flat or planar structure. Second, it should have cyclic clouds of delocalization pi electrons above and below the plane of the molecule. Third, the pi electrons cloud should encompass all the carbon atom of the cyclic system. The total number of pi electrons in the molecular spaces or ion should be 4n plus 2, where n is equals to 0, 1, 2, 3 up to n. These criteria are collectively known as 4n plus 2 rule or simply Huckel rule, or which may be stated as monocyclic planar completely conjugated polyens contain 4n plus 2 pi electrons and having a single cyclic pi electrons cloud encompassing all the carbon atoms in the ring are aromatic in nature. Application of the Huckel rule. Let us now test the validity of this rule. First, 2 pi electron system. The simplest 2 pi electron system is cyclopropene, but 2 pi electrons are not completely delocalized over the 3 carbon atoms of the ring. Therefore, cyclopropene is not aromatic. On the other hand, in cyclopropenyl cation, the 2 pi electrons are completely delocalized. In the light of Huckel rule, it should be aromatic. This has actually been found to be so. In fact, cyclopropenyl cation is quite stable, and the salt of a number of cyclopropenyl cations, such as triphenyl cyclopropenyl cation, have actually been isolated and stored in bottle. Second is the 6 pi electron system. Benzene is a perfect example of an aromatic compound containing a planar hexagonal system of 6 pi electron. Cyclopentadiene contains 4 pi electron, hence it is not aromatic. However, a cyclopentadiene anion is aromatic since it contains delocalized 6 pi electrons and also in planar. Cyclopentacation or cycloheptatrienyl cation or tropylium ion on the other hand is planar and also has 6 electrons which are completely delocalized over the entire cyclic and hence is aromatic. Now our next topic is hydrogen bonding. Definition: when a molecule contains a hydrogen atom linked to highly electronegative atom like fluorine, oxygen and nitrogen, this atom attracts the shared pair of electrons more, and so this end of the molecule becomes slightly negative while the other end becomes slightly positive. The negative end of the molecule attracts the positive end of the other, and the result of electrostatic attraction, a weak bond is formed between them. This bond is called hydrogen bond. It is represented by dotted line as shown in the below figure. Conditions for the hydrogen bonding. First, the molecule must contain a highly electronegative atom linked to H atom. Second, the size of the electronegative atom should be small. Thus, only fluorine, oxygen and nitrogen atoms can form hydrogen bond, as these atoms are smaller in size and have high electronegativity. Chlorine, having the same electronegativity as that of nitrogen, usually do not form hydrogen bond due to its larger strength. Next is the strength of hydrogen bond. Hydrogen bond is a very weak bond. The strength of hydrogen bond is intermediate between the weak van der Waals forces and the strong covalent bond. Thus, whereas the bond dissociation energy of the covalent bond is 209 to 418 kJ per mole, that for hydrogen bond is only 12.6 to 41.8 kJ per mole. The dissociation energy of the hydrogen bond depends upon the attraction of the shared pair electrons and hence the electronegativity of the atom. Next, our topic is types of hydrogen bonding. There are mainly two types of hydrogen bonding. First is intermolecular hydrogen bonding. When bonding takes place between different molecules of the same or different compounds, it is called intermolecular hydrogen bonding. For example, HF, hydrogen fluoride, fluorine have the highest value of electronegativity, that is 4, forms the strongest bond. Hydrogen fluorine does exist as shown as below. Second is water. In water molecule, the highly electronegative oxygen atom that electronegativity is 3.5 is linked to the hydrogen atom. Because of higher electronegativity, the oxygen atom attracts the OH bond towards itself. As a result, oxygen carries a partial negative charge and hydrogen atom carries a partial positive charge. Consequently, the negative end of the molecule of one molecule attracts the positive end of the other molecule, leading to the formation of hydrogen bonds. Third is ammonia. In ammonia molecules, the moderately electronegative atom, nitrogen atom 3 is electronegativity is linked to the hydrogen atom. Fourth is alcohols and the carboxylic acid. Second, we will do intramolecular hydrogen bonding. The hydrogen bonding which takes place within a molecule itself is called intramolecular hydrogen bonding, or we can say chelation. It occurs in compound containing two groups such that one group contain a H atom linked to an electronegative atom and the other group contain a highly electronegative atom linked to a lesser electronegative atom. The bond is formed between the H atoms of one group with the more electronegative atom of other group. For example, the bonding in orthochlorophenol, orthonitrophenol, salicylic acid, and also in 2,6-dihydroxybenzoic acid. Now we will do the conditions for the intramolecular hydrogen bonding. First, the molecule should contain two groups such that one group contain H atoms linked to the highly electronegative and the other group should also contain a highly electronegative atom linked to a lesser electronegative atom. The molecule should be planar. The hydrogen bonding should lead to the formation of either a 5 or 6 member ring, including the hydrogen atom. Now we will do the effects of hydrogen bonding on the physical properties. First, melting. effects of hydrogen bonding on the physical properties. First, melting points and the boiling point. The melting point and boiling point of substance largely depend upon the hydrogen bonding. First, effect of intermolecular hydrogen bonding on the melting and the boiling point. In general, intermolecular hydrogen bonding leads to association of molecules. As a result, such molecules have high melting and the boiling point. First, alcohols. First, we will do comparison of the boiling points of alcohols, ethers, and thioalcohols. The boiling point of alcohols are much higher than those of the corresponding thioalcohols and ethers. The higher boiling point of alcohols than those of the corresponding thioalcohols is due to intermolecular hydrogen bonding, which leads to the association of the alcohol molecules. In contrast, thioalcohols exist as discrete molecules since they do not form hydrogen bonds due to lower electronegativity and bigger size of sulfur, and hence have lower boiling points as compared to those of alcohols. Further, ethers are isomeric with alcohols, but their boiling points are much lower than those of alcohols. This is due to the reason that unlike alcohols, ethers do not form hydrogen bonds. As a result, ethers do not undergo molecular association and hence have lower boiling point than the corresponding alcohol. Similarly, we can explain the boiling point of dihydric, trihydric, and polyhydric alcohols are much higher than that of corresponding ethers. The successive replacement of H atoms of the OH group of polyhydric alcohol by alkyl group reduces the tendency of the resulting ethers to form H bonds, and hence the boiling point of ether decreases as the number of the ether linking increases in spite of increasing in their molecular masses. Second, we will do the comparison of boiling points of water and ethyl alcohol. Both water and ethyl alcohol form intermolecular hydrogen bonding, but still water with lower molecular mass boils at higher temperature than ethyl alcohol with higher molecular mass. This is due to the fact that water undergo a higher degree of hydrogen bonding than ethyl alcohol. As a result, greater number of water molecules are associated as compared to ethyl alcohol molecules, and hence water has higher boiling point than alcohols. Second, we will do amines. Like water and alcohols, primary secondary amines but not the tertiary amines undergo intermolecular hydrogen bonding and hence boil at higher temperature than the isometric tertiary amines. Further, since the electronegativity of nitrogen is lower than that of oxygen, therefore amines form weaker hydrogen bond as compared to alcohols and carboxylic acids. As a result, amines are not associated to the extent to which alcohols and carboxylic acids are associated, and hence boiling point of amines are lower than those of alcohols and carboxylic acids or comparable molecular masses. For example, ethylamine boils at 292 while ethyl alcohol and formic acid boils at 351 and 374 respectively. Second, effect of intramolecular hydrogen bonding on melting and boiling point. Compounds which involve intramolecular hydrogen bonding usually melt or boil at lower temperature than those which involve intermolecular hydrogen bonding. The reason being that intramolecular hydrogen bonding takes place between two orthosubstituted groups and thus prevents association of the molecules. As such, these compounds exist as a discrete molecules, and to melt or boil them only at a small amount of energy is required. For example, orthonitrophenol melts at 317 Kelvin while paranitrophenol melts at 387 Kelvin. Similarly, salicylic acid melts at 431 Kelvin while para-hydroxybenzoic acid melts at 487 Kelvin. In contrast, intramolecular hydrogen bonding is not possible in case of meta and para isomers because the large size of the ring which would be formed. Instead, these isomers undergo intermolecular hydrogen bonding, which cause some degree of association of the molecule. Hence, meta and para isomer melt and boil at higher temperature and their corresponding ortho isomers. For example, ortho dihydroxybenzene melts at 377 Kelvin while dihydroxybenzene means hydroquinone melts at 442. Similarly, orthochlorophenol boils at 446 Kelvin while parachlorophenol boils at 493 Kelvin. Now, water solubility. It has been observed that the compounds which can form hydrogen bonds with water are soluble in water. On the other hand, compounds in which the hydrogen bonding with water is either not possible or is prevented by chelation, or or either less stable or or completely insoluble in water. Thus, organic compounds like alkanes, alkenes, alkynes, halogen derivative, ethers, etc., which are incapable of forming hydrogen bonds with water, are insoluble in water, while alcohols and carboxylic acid, which are capable of forming hydrogen bonds with water, are readily soluble in water. But it may be noted that not all the alcohols are equally soluble in water. Actually, lower alcohols, such as methyl alcohol, ethyl alcohol, and propyl alcohols, are highly soluble in water. But the solubility of higher alcohols with four or more carbon atoms decreases with increase in the molecular masses. The extent of solubility of any alcohol in water depends upon the capability of its molecules to form hydrogen bonds with water. As the molecular mass increases, the hydrocarbon part becomes larger, which resists the formation of hydrogen bonds with water molecule, and hence the solubility goes on decreases. In other words, the solubility of the alcohols in water decreases with lengthening of the carbon chain. Next factor is strength of acids. We know that the strength of an acid depends upon the stability of its ion. Obviously, the strength of the acid should increase if the stability of the anion is increased by chelation. Consider an example: the ionization constant of benzoic acid, salicylic acid, or orthoanic acid. From the above data, it is clear that salicylic acid is about 17 times a stronger acid than benzoic acid and about 13 times stronger than orthoanic acid. This is due to the reason that salicylate ion is stabilized by chelation, but no such stabilization is possible with benzoate ion and anisette ions. Further, greater the stabilization of the ion, stronger is the field. For example, 2,6-dihydroxybenzoic acid is about 800 times a stronger acid than benzoic acid. This is due to the greater stabilization of the ion by chelation with two H groups, which is shown in the below figure. Similarly, we can explain why malic acid is much stronger than fumaric acid. This is due to the reason that malate ion obtained after the loss of proton is stabilized by chelation, but no such chelation is observed in fumarate ion. It may, however, be noted that the second dissociation constant for fumaric acid is much higher than that of malic acid. This is due to the reason that it is very difficult to remove a protein from the chelated malate and thus then form the fumarate ion. Thank you. That's all for that today.